Good day everyone. This is the dataset in my data mining, steel industry and energy consumption. The dataset provided is titled Steel Industry Energy Consumption and contains data collected from a small-scale steel industry located in South Korea, specifically from Daewoo Steel Corporation in Gwangyang. About the dataset. Total instances 35,040. Rows of data. Features 9 variables or columns used to describe each instance. Types of features includes both real, numerical, and categorical non-numerical data. Associated task. This dataset is primarily suited for regression analysis, which means it can be used to predict continuous numerical values like energy consumption levels. Subject area focuses on physics and chemistry, likely related to the process involved in steel production. Missing values. The dataset has no missing values, which means it is completely ready for analysis. Why these datasets? This dataset is chosen due to its relevance in studying energy consumption within the steel industry, which is crucial for several reasons. Industrial efficiency. Understanding how much energy is consumed in the production of steel can help industries optimize their processes, reduce costs, and increase overall efficiency. Environmental impact. The steel industry is a significant consumer of energy, which contributes to carbon emissions. Analyzing this data can support efforts to make steel production more suitable. Economic benefits. By analyzing energy consumption patterns, companies can develop strategies to reduce their electricity bills, thus improving their profit. Optimization of energy usage. With the increasing cost of energy and environmental concerns, optimizing energy usage in industries like steel manufacturing is critical. This dataset provides the necessary data to explore and implement energy-saving measures. Data-driven decision-making. The dataset can be used for predictive modeling, helping stakeholders make data-driven decisions regarding production, schedules, energy procurement, and operational strategies. Benchmarking and analysis. It allows for a detailed analysis of energy consumption patterns which can be benchmarked against other industries or within different time periods, daily, monthly, or yearly. This dataset offers valuable insights into the energy consumption of the steel manufacturing process. It is clean and comprehensive data make it an excellent resource for studies focused on improving industrial energy efficiency and reducing environmental impact. I explained the datasets. Data processing. What preprocess did you need? Before analyzing the data, it is essential to preprocess the dataset. In this case, I employ data cleaning and missing value handling. Data cleaning focuses on correcting errors and ensuring uniformity, while handling missing data involves addressing gaps by either filling them or removing incomplete entities. These preparatory steps are critical for achieving accurate and dependable analysis. Why that process is important? The process used are data cleaning and handling missing data. Data cleaning and handling missing data play a vital role in making the dataset clear and complete. Errors or gaps in the data can result in misleading outcomes or confuse the model during analysis. By correcting inaccuracies and filling in missing values, the dataset becomes accurate and reliable. For the upcoming presentation, I will emphasize evaluating the results of clustering and classification techniques. The analysis will focus on the effectiveness of each method in terms of accuracy, interpretability, and practical applicability. Clustering outcomes will be analyzed based on the coherence of the form groups and their relevance to the problem at hand, while classification performance will be assessed using metrics like accuracy, precision, and recall. This approach will provide a comprehensive perspective of the strengths and limitations of each technique. Comprehensive understanding of how these data mining methods correctly classified instances. 93.75%, 1979 out of 2,111 instances. Incorrectly classified instances, 6.25% or 132 instances. Kappa statistic, 0.927, indicates excellent agreement between prediction and true labels. Error metrics. Mean absolute error, 0.0213. Low average absolute difference between predicted and true classes. Root mean squared error, 0.1286. Relative absolute error, 8.71%. Root relative squared error, 36.77%. Most classes exhibit high precision recall and F measure, above 0.85, showing strong class selectability. The ROC area and PRC area metrics are consistently high, above 0.95 for most classes, indicating excellent performance. The confusion matrix illustrates the actual versus predicted classifications. Diagonal entries for normal weight represent correct classifications. Of diagonal entries indicate misclassifications, misclassified as overweight level. This image is a visualization from Weka Explorer, like generated for clustering or classification analysis. It maps a dataset where the x-axis represents the NSM, or number. Attribute, the y-axis represents day of week, or norm, and the data points are colored based on the load type attribute, which includes three categories: light load, medium load, and maximum load. Cluster explanation. Blue cluster light load predominantly found across all days of the week, with dense coverage indicating that light load is common throughout the week. The distribution suggests that light load is widespread and may not have strong day-specific trends. Red cluster, medium load. Medium load points red appear more concentrated around certain regions on the x-axis, but still span across all days. This cluster indicates periods or instances where a medium load occurs, potentially influenced by a specific range of NSM values. Green cluster, or maximum load. The green points maximum load are less frequent and tend to appear in localized areas, particularly concentrated in specific regions of the x-axis. This suggests that maximum load is rare and occurs under specific conditions, possibly tied to particular NSM ranges. The visualization provides insights into the relationship between load type, light, medium, and maximum, and two attributes, NSM, a numeric parameter, and day of week. The key findings are: light load, blue. This is the most frequent load type and is consistently distributed across all days of the week and across the NSM range. It suggests that light operational loads are the default or most common scenario in the dataset. Medium load, or red. Medium load events occur across all days but show higher concentrations in specific NSM ranges, indicating that medium load is triggered under certain conditions tied to NSM values. Maximum load, or green. Maximum load is the least frequent and occurs only in localized NSM regions. This suggests it is rare and arises under specific circumstances that could potentially indicate peak operational demands. That is how my dataset is experienced and how it is important. Thank you.